All right. Hello, everyone. Today we're going to be talking about structure and bonding, and this will be chapter 1 for this class. So this is sort of our introduction to organic chemistry as a whole. By using our Gen Chem knowledge and our knowledge of how structure and bonding works, that will feed into how organic chemistry works. So the big thing with organic chemistry is these are the atoms and the elements that we'll be mostly talking about in this case, okay? Mostly we'll be talking about carbon and hydrogen, which is not shown here, but carbon and hydrogen. Whenever I talk about atoms that are not carbon or hydrogen, I might refer them as hetero atoms. This just means any atom that's different from carbon and hydrogen. So if I have carbon with 3 hydrogen bonds with a chlorine bond, let's say, the chlorine would be the hetero atom here, okay? So you may be wondering what that drawing was if you took Gen Chem a little while ago. What that drawing was, it was a Lewis structure. Now what a Lewis structure does, it represents the bonds and the lone pairs that are present on an atom. So if we look at a periodic table, we can see that carbon has 4 valence electrons. And we know this because of the column that it's in the periodic table. And we know that oxygen has 6 valence electrons and so on. If you're confused about this, I would recommend looking up a periodic table guide to valence electrons, and that should help sort everything out. But just to reiterate, carbon has 4 valence electrons, oxygen has 6 valence electrons, hydrogen only has 1 valence electron, and these are the 3 atoms that I'm going to use for my example right here. So let's say that a carbon makes a double bond with oxygen, okay? So we can say that the carbon donated 2 of its valence electrons and the oxygen donated 2 of its valence electrons to make 2 bonds, okay? Each one of those bonds has 1 electron from each atom, okay? And then we know that if we take away 2 valence electrons from oxygen, we're left with 4 valence electrons. So we draw that on the oxygen as 2 lone pairs. Okay, and I've drawn this in this specific way because oxygen likes to have 2 bonds for a reason we'll discuss a little bit further. Now, I'm going to erase a little bit. Carbon prefers to have 4 full bonds, so we're going to fill in the rest of its 4 bonds with hydrogens. And notice here how I only have it having 4 bonds. This is because if I had any more bonds, like let's say I had an additional bond right here, this would violate something called the Octet Rule. What the Octet Rule is, it states that every single atom can only have 8 or less electrons around it, except for some special cases such as sulfur, okay? But in most of our cases here, our octet rule is going to apply, so we can only have 8 electrons around an atom, where each bond is 2 electrons and each lone pair is 2 electrons. So we can see here in this carbon, it has 1, 2, 3, 4 bonds. Each of those bonds containing 2 electrons, that equals 8, so we're good. The oxygen has 2 bonds, each with 2 electrons, which is 4, and then it has 4 electrons in lone pairs. So 4 plus 4, that's 8. That is along with the octet rule. And then that's the general idea that we'll be going along with these different Lewis structures. And you'll see me drawing these Lewis structures a lot in this upcoming chapter. If you are confused about it, just either let me know in the comments, send me a message, do anything that you need, and I can go ahead and make a dedicated video on Lewis structures if you really, really need it, or I can answer any questions that you may have. All right, so let's go on to the periodic table. So here is a periodic table with most of the stuff that we'll be using in this class. The main focus, again, is going to be carbon and hydrogen. Okay, and one thing to note here, we can tell how many valence structures something has by looking at its group number. So fluorine, chlorine, bromine, iodine, they're going to have 7 valence electrons. Oxygen and sulfur have 6. Nitrogen and phosphorus have 5, and so on, okay? And so then that's generally how we see things. And this stuff here, this is just Gen Chem stuff. I'm going to go ahead and assume that you know how to do that, but we will talk about it more later chapters when we talk about spectroscopy and the like. It's just understanding that when we have a carbon or any atom represented like this, the top number is going to be our mass number, the bottom number is going to be our atomic number, and the mass number can change, and these are called isotopes because they have differing number of neutrons, but the atomic number will always stay the same. Just go back, review Gen Chem stuff if you're confused by this. All right, so now let's go into something called atomic orbitals. This is something that not a lot of people remember, but it's that thing where we had 1s, 2p, 2s, or 1s, 2s, 2p, 6, and so on. And so each one of those different orbitals, s, p, and d, so on, but right now we're only going to be focusing on s and p, specifically 2s and 2p. So we can see here that an s orbital looks like just a regular circle, a regular sphere. And 2p, any 2p orbital looks like two balloons tied to each other. That's the best reference that I can get, where each orbital or each part of the orbital is on a different part of the node. And the node here is just the very center of those two orbitals and the very center of the sphere here. Now, when we're talking about organic chemistry, we are referring to orbitals. We're generally going to be talking about how orbitals combined to make hybrid orbitals that make up our bonds, okay? And if you are doing the ALEX right now, or if you don't know what I'm talking about, then you can just sort of skip over this. The ALEX has a lot of question on orbitals and stuff. If you want, again, I'll probably end up making a dedicated ALEX video about orbitals themselves, but honestly, for now, for this class, this is all you need to know. These orbitals, s and p, will combine to make something called hybrid orbitals, which are either called sp, sp2, or sp3. And where do we get these numbers is dependent on how many electron groups that a specific carbon has around it. So if we scroll down a little bit, we can see that, again, orbitals and shells, this is stuff from Gen Chem. I'm not going to focus on it here because it's not as important for this class. The main thing we're going to be focusing on, again, is the hybrid orbitals with sp and sp2, etc. So we can see here that each one of these different groups here, or each one of these different atoms here, they all have 4 electron groups around them. When I say electron groups, I mean either a bond or a lone pair. A single electron group can also be 2 bonds, or it can be 3 bonds. These are each considered a single electron group. Each one of these here has 4 electron groups, okay? And so then we consider all of these to be sp3 hybridized, because it has 4 electron groups around it. And the best way that I remember this is you have 1s plus 3p, that equals 4 total electron groups, okay? And so then each one of these, with their specific number of bonds and their specific number of lone pairs, has to do with something called the formal charge. So when you're sp3 hybridized, generally you're going to be neutrally charged. Okay, and this has to do with the formal charge of a specific atom. If you recall, the formal charge, so F, formal charge, Fc, equals the number of valence electrons around that atom minus the number of bonds that it has, and then minus the number of electrons in the lone pairs. So let's take carbon as an example here. So its formal charge, or this example specifically, would be 4 valence electrons minus 4 bonds minus 0 electrons in lone pairs. So that means that its charge is 0 and it's overall neutral. And also we can see that it's sp3 hybridized. When we look at nitrogen, we know that nitrogen starts out with 5 valence electrons, and in this case it has 3 bonds and 2 lone pairs, 2 electrons in lone pairs. 5 minus 3 minus 2 is 0, so it's neutrally charged. And you can do this also with oxygen and X. X is just any halogen, as you can see here. So that's why when you're sp3, you're going to generally be neutrally charged, because your formal charge is going to match what you want, what each atom wants to have a neutral charge, okay? So Like we said before, sp3, I'm going to skip past this stuff a little bit because it's talking about formal charges, which we just talked about. And this goes on to talk about how you can see that when you're not sp3 hybridized, you have other formal charges. But what I want to talk about a little bit is how do we know if something's sp2 or sp? We are going to use the same convention that we did when we figured out when something is sp3. We have one s group plus 3 p groups, which means we have 4 electron groups total for sp3. In sp2, we have one s group plus 2 p groups, so we have 3 electron groups total around the atom. sp equals 1 s group plus 1 p group. We have 2 electron groups total around the atom. So an example of sp3, again, like we saw before, was carbon with 4 bonds. Another example of an sp3 would be oxygen with 2 lone pairs and 2 single bonds. So now let's go on to sp2. So if I drew a carbon with 3 bonds around it regularly, then that would be an sp2 hybridized. But we also have to notice that this guy is going to have a formal charge of +1 because, recall, valence electrons minus the number of electrons in bonds minus the number of electrons in lone pairs. In this case, carbon has 4 valence electrons minus 3 bonds minus 0 lone pairs. That equals +1. This is something called a carbocation, which you're probably going to end up seeing a lot more in organic chemistry as a whole. But in this case, we are just looking at it for its sp2 character. Another example of a carbon with sp2 would be a carbon that has a double bond anywhere. So this double bond could be on top here or on the left side, but right now I just have it drawn on the right side. And again, remember we consider electron groups as either a double bond, a single bond, or also a triple bond and a lone pair, okay? And then the final example I want to do for an sp2 hybridized atom is oxygen with a double bond. And this oxygen is neutrally charged because remember, formal charge, valence electrons, of which oxygen has 6, minus the number of bonds, in this case 2. Now notice here how we consider each bond separately when we're calculating the formal charge. However, when we discover if something's sp3 or sp2 or sp, we count double bonds and triple bonds as one electron group. So here we can see the big distinction between formal charge and sp, sp2, sp3 character. So in this case, 6 minus 2 bonds minus 4 electrons in lone pairs, that equals 0. We can do the same thing with this carbon right here. 4 minus 4 bonds minus 0 electrons in lone pairs equals 0. So this one's also neutral, okay? So now let's go on to sp. sp, similar to how sp2 has a double bond somewhere for carbon, it's going to have a triple bond somewhere with carbon. So this triple bond can be to another carbon, it could be to a nitrogen, it could be to anything, as long as it has a triple bond somewhere. And then this can be bonded to a hydrogen. Usually it's bonded to a hydrogen, but it also can be bonded to a carbon or anything else. And we can also see sp2, not sp2, sp being carbon with a triple bond and a lone pair. But then this would be negatively charged because if we pull up the formal charge, 4 minus 3 bonds minus 2 electrons in lone pairs equals -1. So this guy is going to be negatively charged and sp hybridized. Okay, and I'm not really going to do an example with oxygen right here because we don't usually see that. The most that we'll see that with is something called resonant structures, which I'll get into a little bit further. I'm sure you've heard of this before in Gen Chem, but again, I want to give you guys a refresher on all of your Gen Chem stuff that's going to be relevant in organic chemistry. Okay? So that was sp3, sp2, sp, and all the examples with it. So now let's talk about something called constitutional isomers. So constitutional isomers are the same molecule overall, but they have different connections. So in this example, C2H6O, both of these have the exact same total number of carbons, hydrogens, and oxygens. It's just that this one has oxygen over on the side bonded to a hydrogen, whereas this one has oxygen in the middle of 2 carbons. So these are called different sigma bond connections. And all a sigma bond means is your single bonds have different connections. And let's just reiterate what a sigma versus pi bond is. A sigma bond is your single bond, where your pi bond is any bond additional to that. So if we have a triple bond, we have 1 sigma bond, this is the symbol for sigma, and 2 pi bonds. That's the symbol for pi. Sorry, I misspoke there. And then for a double bond, we have 1 sigma and 1 pi. So the movement of the sigma bonds, which is the single bonds part in particular, is what makes constitutional isomers different. The movement of pi bonds has to do with something called resonant structures. So notice here how this guy on the left, right here, this guy has a double bond from C to oxygen. In that double bond, we have 1 sigma bond and 1 pi bond. And then when we go to our other resonant structure, we can see that that pi bond has moved to be next to the nitrogen. This sigma bond is still here. The pi bond is what moved. In addition, the connections overall of the sigma bonds are exactly the same between 2 resonant structures. The only thing that changes is where the electrons and lone pairs are and where the double bonds are. So if I were to draw how the electrons move, I'm going to use full-headed arrows, so arrows like this, to represent the movement of 2 full electrons. So in this resonant structure case, 2 full electrons from this double bond move to go on that oxygen, okay? And then 2 electrons from this nitrogen move to make a new pi bond with that carbon. And notice here how this carbon is sp2 hybridized. And remember that when we're sp2 hybridized carbon, it's going to have a double bond somewhere. It does not care where, as long as it has that double bond. So it doesn't really differentiate or prefer this double bond over this double bond. And so either one of these can be seen. When we talk about resonant structures and a compound's quote-unquote true structure, the true structure of a compound is going to be sort of a hybrid between these two, where the double bond is switching between the two so fast, we only ever see like a partial bond here or a partial bond there. And so if I were to draw how the same arrows like I did over here with this right resonant structure, you can see here that this double bond breaks, goes on the nitrogen, and then a free lone pair of electrons from the oxygen goes to that bond and makes a new bond. I know it can be kind of hard to see resonant structures when you're first beginning, but it's going to become a lot easier to see once you start practicing. Like once you understand the fact that sp2 carbons can have a double bond anywhere, and so that pi bond is free to move, then it might make a little bit more sense once you do some more practice problems. Okay, and we can see here that these two are not resonant structures. These two are constitutional isomers, because we can see that sigma bond paired with that hydrogen there move from the oxygen to the carbon. So these two are constitutional isomers, and you should be able to differentiate it between resonant structures and constitutional isomers. And if somebody asks you, hey, is this a constitutional isomer, a resonant structure, or the same thing between the two of them, you should be able to tell. Okay, so again, now we're going to talk a little bit about resonance hybrids. Again, when we're looking at a compound's quote-unquote true structure, it's going to have a hybrid between its 2 resonant structures where it has partial bonds, or partial pi bonds, where those pi bonds move, okay, and partial negative charges. This overall makes the compound more stable because it sort of delocalizes the negative charge across the whole molecule. Because if you think about it, let's say that I have a stick with a ball on it. If the ball has all of the negative charges, it's going to attract a lot more positive charges. However, if instead the negative charge was distributed all across the stick, it's going to attract less positive charges. So it's going to be more stable overall. And so then this guy is preferred. More resonant structures means you're more stable. Okay? Again, I talk about this a little bit more in my acid-base review for chapter 2 in this class. Just go back and look at that if you're a little bit confused. So, oh, and one more thing to note here is atoms never move. And we can also see that reflected in how I draw the arrows. The arrows always go from either an electron pair or from a bond. okay? And they always go from electron pair to either another bond or an atom. And the same thing with the bonds, a bond or another atom. Okay, so we show how electrons move with arrows. We do not show how atoms move with arrows. Okay, all right. And so then here's just examples of how we draw resonance structures. Again, we can see here, in this case, number 3, you may be wondering why this is invalid. We can see here that this second resonance structures, it invalidates the octet rule. And so that's another important thing to note. Resonance structures cannot violate the octet rule because this carbon, it has 5 bonds times 2 electrons per bond. That's 10 electrons. That's more than 8. It violates the octet rule. Okay? So now let's talk about molecular geometry. So remember when we talked about sp2, sp3, and sp, we were talking about the number of electron groups around it. sp3 has 4 electron groups around it, sp2 has 2, and sp has 1. So they're directly related to these geometries: linear, trigonal planar, tetrahedral. And we can sort of represent these different geometries with some sort of different drawings. So you may have seen something called a line angle structure when you've been reading your notes, reading your textbook, or whatever. Again, we'll get into that in just a hot second. We can see here that when we draw the linear version of a triple bond, instead of drawing it with points like this, we draw it straight to represent its linear geometry, okay? And you'll see a bit later when we talk more about stereochemistry or how an atom fits in space, we draw tetrahedral atoms like this, where each line represents a atom or a bond in the plane. A solid wedge represents a atom or a bond coming out from the screen towards you, and a dashed wedge shows an atom or a bond going into the screen away from you, okay? And again, we'll talk about that more later when it becomes more relevant, but right now, I want to talk about something called a line angle structure. So the line angle structure is essentially a representation of our Lewis structure that's broken down in a simpler form so it's faster to draw. So the general idea for a line angle structure is that at every one of these points or ends of a line, there is a carbon. In addition, at every one of those carbons, there are invisible hydrogens, making sure that every single neutral carbon has 4 full bonds, okay? So these carbons in the middle have 2 hydrogens each, and these carbons on the end have 3 hydrogens each, okay? And so if I were to draw this in its molecular formula, I would say this is CH3 attached to parentheses 1, 2, 3, 4, CH2s 4 times attached to their CH3. Okay? So that's how you sort of write the condensed formula. It's telling you what's on either side of an atom. So let's say that I drew the line angle structure of this guy right here. I would say, okay, let me count my carbons. I have 1, 2, 3, 4, 5, 6, 7, 8 carbons. It's important to note that this carbon at the end here, I sort of drew it kind of badly. This carbon at the end here is also another carbon. On either side of this triple bond, there are 2 carbons, but in addition to that, there are carbons attached to those 2 carbons. This will become more clear when we talk more about alkynes, aka stuff with carbon-carbon triple bonds, okay? So now if I were to write this out, I can see that this guy here is going to be CH3. This one's also going to be a CH3. So I would write CH3, 2, because we have a CH3 2 times. And this one here, I'm going to say that's a CH, only once, because to fill in its octet and to give it 4 hydrogens, 4 bonds total, we're going to need to add in 1 hydrogen. Okay? And I'm going to say this guy, oh, this is also a CH, because again, hydrogen bonds. And then this one's a CH. Okay? So technically, you can put CH3 to CH 3 times, but I'm just going to say that I prefer this one. And sometimes you'll see that double bond drawn into the condensed formula name. And the reason why I prefer this one is because the CHs, these three CHs, are not all equivalent. So it just depends on what you prefer, what your professor prefers, what your book prefers. But I prefer this one where we also draw in the double bond. So then we draw this guy right here, this carbon. This is just a carbon, just a regular carbon, because we can't have an additional bond there or we would be violating the octet rule. Same with the other one there. And then finally, we have a CH3. So that was sort of a harder version of probably most of the stuff that you're going to be asked to do, but I find it sort of important to do the harder problems before you're asked to do them. All right, so that's basically how you do a line angle structure. So let's talk a little bit about the different bond lengths. So bond lengths are directly related to how many bonds you have surrounding a particular atom. So we can see here that this one has 4 bonds around it. So it's going to have the largest bond length. So it's sort of like this carbon is sharing its strength with 4 other things. So it's going to hold on to those leashes, quote unquote, those bonds, those leashes, a little less tightly than something with only 3 leashes. And that's going to hold on to stuff a little less tightly than those with 2 leashes. Okay? And so then that's why generally when you have more bonds on a single atom, the longer those bonds are going to be. In addition, we can see here that the more electronegative something is, so fluorine is the most electronegative here, and Br is the least electronegative thing here. So the bigger the electronegative difference, the more partial positive or partial negative charges you'll have, and the more those 2 different atoms will be attracted to each other, and the shorter the bond will be. So we can see here, Br, with its lowest electronegativity compared to hydrogen, is going to have the longest bond, and then chlorine, and then fluorine. All right. So again, this is talking about the linear geometry of an sp2 carbon. This is talking about the trigonal planar geometry of an sp2 carbon. So the reason that we have the reason why we have all these electron groups or molecular geometry groups is because the way that the bonds are set up in 3-dimensional space is to give the electron groups as much room as possible away from one another. So obviously to be as far apart from one another, if you only have 2 groups, is to be in a straight line. When you have 3 groups, then it's going to be in a single plane as a triangle. Okay, and finally, if you have 4 electron groups, it would be in the tetrahedral formation. And so something to note here is that when you do linear, that's 180 degrees, obviously, because it's just a line. Trigonal planar, 120 degrees, because it's a triangle. And then tetrahedral has 109.5 degrees. These numbers are pretty important to remember, both for random test, and the ACS and your MCAT, if you're planning on taking that. So just sort of keep in mind these things, okay? And also those angles can change depending on if you have either a bond or a lone electron pair, because generally a lone electron pair is going to fight for more room than just regular bonds. And this is stuff from Gen Chem. Again, review it if you're having a little bit of trouble understanding me. Okay. So again, we're going on to talk about line angle structure and hybridized atomic orbitals. I'm just going to continue on. Oh, and this is sort of explaining why we do our hybridized atomic orbitals, but it's sort of the same explanation that I did, where sp3 has 4 electron groups, sp2 has 3, sp has 2. Okay? So yeah. I think that's about it for chapter 1, structure and bonding. If you have any questions, again, feel free to comment or send me a question. Oh, and one more thing. As you increase an S character, so let's say SP, SP2, and SP3, as you increase an S character, which is the percent amount of S that you have in the bond, so SP, we have 1S, 1P, that's 50% S. SP2, 1S, 2Ps, that's 33% S. And finally, SP3, 1S, 3Ps, that is 25% S. So we can see here that those with the lowest S character are going to have the longest bond, and those with the highest S character are going to have the shortest bond. And again, this sort of has to do with that carbon, that sp3 carbon, is going to have 4 different bonds or leashes that it has to hold on to, whereas an sp carbon only has 2 different bonds it has to worry about, or 2 different electron groups, okay? So bond polarity, this is just going into what I said earlier about the bigger the polar difference between electronegativities between atoms, the more tightly they're going to hold onto each other, because they'll have something called a dipole moment. Okay, and I think that's about it for this chapter. Again, and I want to talk about one more thing. Let's say that we're given a structure like this, like from before. It's a little bit different. And I were to ask you, what are the orbitals that make up this bond? When I ask this question, I'm just asking you, what are the orbitals of each atom that makes up these bonds? So in this case, that would be this C attached to a triple bond, and then a single bond to a carbon, which has 4 bonds, 3 of them being to H's. And so then that carbon with the triple bond will be sp, as we've discussed earlier. And we're going to put CSP because that tells us it's a carbon sp bond. And we can say here that this one is a carbon sp3 bond. Sometimes you won't see the C, sometimes you'll just see sp3. That'll usually be fine because it's sort of implied what atom you're talking about if you're talking about this specific bond, okay? And let's say that we were then talking about this bond right here. I'm going to go ahead and draw in those lone pairs for oxygen. We know that this carbon here is going to be carbon sp2, and then we know that this oxygen right here is going to be an oxygen sp2. You can also write this sp2, sp2. Okay, and the one last thing to note is that hydrogens, so like a hydrogen right here, is always going to be hydrogen S because they don't have any other orbitals to make a hybrid with. So if I asked you, what are the orbitals that make up this bond? You would say HS bonded to carbon sp3. Okay? All right, so I think that's about it for chapter 1. Just let me know if you have any other questions or if you need me to make another video on anything in particular that I talked about during this little review session for Gen Chem and going into organic chemistry. Have a great day.